See, this example comes a little later, so let's go back to see these notes. See, this is what's on Blackboard, Chapter 17, Part 3. We've looked at example 1, 2, 3, and 4. Okay, so let's look a little further here where we talk about the solubility product constant. This is similar to the example we just did, but let's look at this reaction, lead sulfate dissociating into lead 2+ and sulfate. So it's a standard example of a KSP type of reaction, solid on the left, just dissociating into its ions. So let's suppose we make a galvanic cell, or in other words, like a laboratory battery. And we want to set it up in such a way that we can measure KSP from the cell. So what we could do is set up the cell to have lead on one side and, for example, tin on the other side. And we need to keep the concentrations of things that aren't involved, like tin 2+, fixed at 1 molar. And on the lead side, we're interested in solubility of lead sulfate. So we would need to add sulfate to precipitate lead sulfate, because the equation here is in equilibrium. We have to have solid lead sulfate in the beaker or the cell compartment in order to be in equilibrium with its ions. So we need to add enough sulfate on the lead side to cause a precipitate. Okay, so let's suppose we did that. And after the precipitate form, we increase the concentration of sulfate to 1 molar. That step isn't necessarily required, but it makes it simpler to do the calculation. So we have these half reactions, the lead and the tin, and the cell potential is found to be positive 0.22 volts with lead at the anode. And that tells us, or we know that because we hooked a voltmeter to it, and the current flowed from the anode to the cathode that registers as a positive current or positive voltage on a voltmeter. Here are the standard reduction potentials for each half cell. So what we need to do is rearrange these in such a way that, let's see, we have lead. We're going to oxidize the lead, so that reverses the sign. We get plus 0.13 volts. We'll keep the tin being reduced at minus 0.14 volts. And the overall cell reaction would be the sum of those two, which would be minus 0.01 volts. So now everything that's known can be substituted into the Nernst equation. This equation we went over in part 2 last Wednesday. We're taking the natural log of the equilibrium constant. For this reaction, we have lead 2+ on top and tin 2+ on the bottom, and the solids don't appear. So if we plug everything in, we get natural log of the lead concentration. It's minus 18. That's all based on the E0 value was minus 0.01 volts, and the observed E value was 0.22. So under those conditions, The concentration of the lead is e to the minus 18th power, which is 1.5 times 10 to the minus 8 molar. So this is one of the two pieces to the puzzle we need to calculate a KSP. KSP is the concentration of the lead times the concentration of the sulfate. And we know the concentration of the sulfate because it was fixed at 1 molar, which makes the math easy. So we take what we found for lead, 2 plus, 1.8 times 10 to the minus 8 times 1, and that gives us KSP of, that's a typo, there should be an 8 there. Oops. So yeah, so scratch through the 1.5 and put a 1.8 there. So and this value is close to what's in the tables for the KSP of lead sulfate, which is around 2 times 10 to the minus 8. And normally there is some difference here depending on the experimental error and rounding and things like that. So sometimes the calculated values can be a little bit off from what's in the table, but usually those differences aren't significant. Okay, so let's look at the next example, which is also about KSP. Okay, so in this example, we have a cell employing the standard hydrogen electrode. It's the one we talked about last time. It's also known as the SHE electrode, SHE. And the other compartment contains a lead electrode with 0.1 molar potassium chromate in contact with solid lead chromate. So this is like the previous example where we have a solid inside the cell in equilibrium with its ion. So the potential of this cell is measured at 0.51 volts, with lead being the anode. So from that information, let's figure out what KSP is for lead chromate. So we start out like we did before with the standard reduction potentials for the two electrodes. The lead reduction is minus 0.13 volts, and then the SHE electrode reaction involves H plus and H2, written as a reduction that's set to 0 volts. So now let's rearrange that to a spontaneous form. So that would be oxidizing the lead. And when we do that, we change the minus to a positive here. So it's plus 0.13 volts. And versus the SHE reduction, it's still 0 volts. So it gives us an overall cell reaction of plus 0.13 volts. So let's look at the Nernst equation. It's one just like in the last example, where we have the equilibrium constant expression as lead on top and H plus on the bottom. And the other parts like H2 gas, that's kept at 1 atmosphere in the SHE electrode. So that does not, well, it's actually a numeric value of 1, so it doesn't affect anything here. And lead is a solid on the left, so that doesn't appear. So the equilibrium constant involves only 2 items, lead 2 plus and H plus. So let's plug in what we know. Firstly, we know the overall cell reaction was observed or measured. It says here 0.51 volts. That's what E is. E0 is the value when everything is at 1 molar here, and that's positive 0.13 volts. And then the equilibrium constant has a concentration of H plus on the bottom at 1. That's another characteristic of the standard hydrogen electrode. H plus concentration is set to 1, which makes us simple math here. So the only unknown is the lead in the log term. So natural log of lead is equal to this stuff on the right, which is, after doing some algebra here on the left, it ends up on the right. And that ends up being minus 29.57. So we take the exponential of both sides. We end up with the lead concentration being 1.4 times 10 to the minus 13 molar. So now we can calculate KSP. KSP is the concentration of the lead, which we've just found out, and times the concentration of the chromate, which is given up here. Potassium dichromate is a soluble salt, so it dissolves completely, yielding 0.1 molar chromate ion. So we plug in what we've found out. Lead is 1.4 times 10 to the minus 13 molar. The chromate is 0.1 molar. Multiply them and we get 1.4 times 10 to the minus 14. And that is pretty close to the given answer. It differs only slightly, because of rounding, most likely. Like technically in some of these places we would use, like here, we'd use a minus 30. And because we have 2 sig figs here in the 0.38 volts, so we would round this technically to minus 30. That would change this answer. So for reasons like that, there are subtle differences in the calculated KSPs. I worked it out here so that it was reasonably close to what the author had in their example. Okay, so let's see the next one. It involves calculating pH. That's back here. pH measurement. So another thing we could do is measure pH. Notice in this last example here, notice that we have H plus in the Nernst equation. We could fix the cell so that we can measure H plus if we wanted to. So it would involve like adjusting the standard hydrogen electrode so that H plus isn't always 1 molar. But we could do that and make a pH meter, which is actually how one of those works. So let's look at the Nernst equation as applied to measurement of pH. So let's look at a copper hydrogen couple here. So for this reaction, copper aqueous reacting with hydrogen gas, yielding copper solid and H plus. The Nernst equation has this form. So we have H plus on top, it's squared. And on the bottom, we have the copper ion and the partial pressure of H2. And we can build the cell such that the copper concentration is 1 molar, the partial pressure of hydrogen is 1 atmosphere. So that'll set the denominator equal to 1 times 1. So the denominator becomes 1 and disappears. So it makes a simpler expression here. So the E is equal to constants times the natural log of the H plus concentration. And it's squared, so we could bring that 2 out front of the log and absorb that into our constant. So it doubles the 0.0257. We get 0.0514. And we end up with this expression if we convert the natural log to a log. In order to do that, we multiply by 2.303 So that gets absorbed into the constant. So we have log here, base 10 log instead of natural log. And we have a minus log concentration of pH, concentration of H plus, which is a definition of pH. So now we can relate the voltage E to pH. So we have this handy expression here, and we can use that to measure pH with a lab battery. And this has a simple form for a given reaction that is a given number of moles of electrons, where N is some fixed number. It's E is equal to some constant. The constant is E0 plus a slope times the pH. So this is the equation of a straight line. It's a linear function of pH. So we can rig up a little instrument to calibrate, like take two pH measurements on standards, like a pH of 4 and a pH of 10, calibrate, and the calibration will fix the constant and the slope term. So then we can measure any pH in between with that instrument. All right, so let's look at an example of that, example 6. So here we have a galvanic cell. Here we have copper versus the standard hydrogen electrode. And it's just like the one we went over. We fix the copper concentration at 1 molar. Pressure of H2 is 1 atmosphere. And then we measured a voltage of 0.48 volts. So from that information, let's calculate the pH. So we start out again with the standard reduction potentials. So here we have copper and hydrogen. So we rearrange these to a spontaneous form. Copper had the most positive E0 value, so we keep that as is and reverse the other. So the hydrogen gas is oxidized, and that gives us a cell voltage of, or an E0 value of plus 0.34 volts. So let's look at the Nernst equation for pH, which we just derived, and plug in these values. So E was observed to be 0.48 volts, so we plug that in. E0 is 0.34. The 0.118 on 2, that's part of the derivation. We have 2 moles of electrons in this case. And all that times the pH. So we know everything in here except the pH. So let's figure out what pH is. So algebraically, we solve for pH. And it comes out to 2.37. So that would be an example of calculating pH. Okay, let's look at the next example. A flashlight battery. One of the most practical applications of chemistry is a battery. And a Duracell flashlight battery, for example, has this label. It's D, type D battery, MN 1300. That means manganese base, and their version of this battery is 1300. Manganese oxide has a potential of 1.5 volts typically, and LR20, not sure what that means, might have to do with the size of the cell. So if we go to Duracell's website, if we wanted to figure out what all this means, let's see, we could click on that, see if this link works. That doesn't work, but anyway, the screenshot was pasted in here. So this is what the spec sheet for this battery looks like. It shows us the nominal voltage, 1.5 volts, the volume and the weight. Their goal, the goal of any battery manufacturer is to have the highest energy and the least amount of weight. Okay, so here on the right, we have dimensions. So here's a typical discharge curve for a battery. And you've probably noticed when using a battery that how long it lasts depends on how fast it's used. Like for example, if we had a flashlight battery and it's put in a flashlight, and then the flashlight is used continuously for like an entire evening or night. Like if you're out hiking at night or something and use a flashlight continuously all night, it's not going to last very long, right? And if it's also put in a flashlight that has this huge light bulb that shines like 500 feet away, it drains a lot of current out of the battery, and that'll use it up pretty quick. So these discharge curves here measure the voltage as a function of time and hours. Service hours is how long the battery was actually used. So see the voltage here, whenever only 250 milliamps is drained from it, that's like through a small flashlight light bulb. So the voltage decreases, and after an hour or so, it's like 1.45. After 2 or 3 hours, it's at 1.4. The voltage keeps going down. The light will get dimmer and dimmer until finally it drops below 1 volt after about 46 hours. And then essentially after 50 hours, it's pretty useless. There's no more juice in the battery. So that this curve measures the capacity of the battery. So if the purple line here is if we double the discharge rate, that is, instead of 250, we go to 500 milliamps of current. So we're draining it twice as fast. That's like using a bulb that's twice as bright. So the voltage drops much more steeply, and after only about 20 hours, the thing's exhausted. And if we double it again and go to 1,000 milliamps, see the voltage drops off really fast. And we can go even farther, but let's calculate the capacity. And the capacity of a battery is measured in current times time. So it'd be the milliamps as the current times the time in service hours. The equation is the capacity is equal to the current times delta T. So at the capacity at 250 milliamps of discharge rate is the current 250 milliamps times 50 hours, and we get the 50 hours from here, the last part of the graph, where it ends up at the bottom 0.8, that's at 50 hours. So the current times the time is 250 times 50 is 12,500 milliamp hours. So that would be the capacity of this D battery at a discharge rate of 250 milliamps. Now it's calculated at 500, and that is a service hour of 19 hours, and that comes out to 9,500 milliamp hours. And at 1,000, it's way over here. It's only like 6.5 hours, so that comes out to 6,500 milliamp hours. So see, the capacity of the battery goes down pretty steeply depending on how much current is drained from it. We could go even farther, like here they did 1,500 and 2,000 milliamps and calculate the capacities there. At 1,500 milliamps, its service life is only like 3.5 hours. So that's 5,100 milliamp hours. And at 2,000 milliamps, it's only 2 hours. So if we compare the 250 to all the way down to the 2,000, we can see that it drops off pretty strongly depending on the current rate. See, it's not quite the end, but there's a couple things here. Let's see, also related to batteries. Yeah, let's start here. Like, you'll need to know the standard notation for cells. Like in a lab battery, we would have the anode and cathode in separate beakers. And a salt bridge would connect them. And the salt bridge just allows ions to travel from one to the other. In a real battery, we have an anode that could be like a graphite post, and then we would wrap it in a separator. It's a piece of porous plastic that functions as a salt bridge. And then on the other side of that separator, we would wind around a sheet of cathode, like a copper foil or something, and then put it in a can, put ends on it. And in a nutshell, that would be our battery. But in a lab, we make them with beakers so we can experiment. So in a battery, the electrons flow from anode to cathode. The cathode is a positive battery. It's always where reduction occurs. Here, copper 2+ is in solution. It's a stable metal, so it's going to reduce to copper 0 on the cathode. And it gets its electron that it's reduced from over here, the anode, where zinc dissolves. Zinc 2+ goes into solution, and the 2 electrons go through the wire and over to the cathode, where they are picked up by the copper. And the notation for the cell is always written with the anode on the left, cathode on the right. So in literature, we'll see this sort of notation, minus where it explicitly says anode and cathode, of course. So we know by looking at it that zinc solid is the anode, and it's in contact with zinc 2+ ion. The 2 vertical lines mean separator, or in this case, a salt bridge. And next we have the ion in contact with the cathode, and the cathode is solid copper. So from this sort of notation, you need to know like how to draw a battery. And we have many classifications of use for batteries. They're all different sizes, and in addition to capacity, we measure them in terms of energy. So capacity is milliamp hours. Energy, it would be milliwatt hours. Or it doesn't necessarily have to be milli, it could be regular watt hours, or it could be kilowatt hours. Like your electric meter in your house measures energy in terms of kilowatt hours, or it could be megawatt hours if it's a really huge one. Like a kilowatt hour size battery would be like for an electric vehicle. And one that's milliwatt hours would be the miniature batteries, such as for electric watches, calculators, or defibrillators and things like that. If we go to watt hours, that would be batteries for portable equipment like flashlights, toys, laptops, camcorders, cameras, and stuff like that. If we go to watt hours, that would be like a battery that could start a car or a lawnmower. And then an electric vehicle battery would be kilowatt hours. Megawatt or high here it's 250 watt hours to 5 megawatt hours would be like emergency power supplies. And The largest are load leveling batteries, which go up to 100 megawatt hours. And for the D battery example we looked at, that's an example of a non-rechargeable cell. In the lingo, those are called primary batteries. Secondary batteries are rechargeable, like the lithium battery in your cell phone or your laptop. That would be secondary. Flashlight batteries, toy batteries are usually non-rechargeable. They're primaries. So the letter tells what size it is. Like a D battery is supposed to have dimensions of 57 by 32 millimeters, roughly, be the diameter and the height of the can. Like AAA is only like 43 millimeters by about 10 millimeters. So this chart here just describes the size of all the battery cans. And button cells, as you probably know, have all different kinds of sizes depending on their capacity. Like the smallest capacities, like for a watch, might be only 2 millimeters by about 10 millimeters, like 2 millimeters thick by about 10 millimeters across. And these are all circular, so the dimensions are height by diameter. Okay, and so we've already looked at this. Let's have a look at that link. Oh, by the way, this guy is Walther Nernst. He invented the Nernst equation, in case you're wondering. This is a data sheet for Duracell. Yeah, so they have all different, like everything they make is here. You can download the spec sheets. Like here's their D, MN 1300. That's what I had copy pasted. Like for example, here's their MN 2400 AAA. Could have a look at that. So this gives the same sort of information for their AAA battery. So they have the same sort of curves here, the drain time, like the discharge curves for various current rates. So it drops off pretty fast with load, just like the D battery did. So it's a standard trait of most batteries. Okay, so that's pretty much at the end of this third part here of the notes. Okay. Anyone home?
Mic on.
Hello?
Yep, I'm here. I'm
Yes.
back after my internet died.
Okay, stop the recording. Okay, does anyone have questions, or I'll post the recording whenever Microsoft sends it. I always post a silent version where it goes through all the PowerPoints. So